Hello, welcome again to another session of Operating System Concept. For today, we are going to look at memory management. So for today, we are going to look at some of the basic requirements of memory management and why we need memory management for the operating system. This is followed by the concept of memory partitioning, and lastly, we are going to look at address, paging, and segmentation in memory management. So now, on to part 1, which is memory management requirement, which simply put as why do we actually need memory management and what are the requirements needed for memory management. As you may remember, memory is one of the important resources aside from input-output devices and CPU time. So that's why this chapter is dedicated for you to understand how memory is being managed by the operating system. First and foremost, let us get to know the requirements that is needed by the operating system in order for it to do memory management successfully. First of all, it needs to specify the relocation requirement, followed by the protection requirement, sharing requirement, logical organization requirement, and physical organization. So briefly, relocation is on when we actually move the processes from the secondary memory into the main memory. Remember, during the process states change, there are the swapping in and swapping out of processes. So this is where the relocation requirement must be satisfied. And then secondly, the requirement of protection. It simply means that in order for process to be swapping in and swapping out into this location, it must have the correct permission, and each process cannot actually interfere with the other process that is actually allocating a certain spot in the main memory. Third, of course, is the sharing capabilities. It means that when we are actually loading these processes into the memory location, it is good to have the sharing capabilities where we can share data, and perhaps this data can be reused by other similar processes, provided it has the correct permission to do it. Fourth, of course, is the capability of having a logical organization and the physical organization. Okay, the concept of logical and physical organization is that logical organization is what we see as the user. Usually, logical organization is being put to be simply having a visual representation of the memory that is easily understood by the user. For example, we have the pie chart of the memory availability that we see how many percent of memory which is already available. But at the other side, we have the physical organization here, where we have the actual location of the memory that is scattered around in the main memory. Of course, it's not pretty because the availability of those spots in the main memory is usually being organized by the operating system. Only that while organizing this location, OS actually keep track of how many spots in the main memory is still available, and it is given in a logical representation so that the user can easily understand or keep track of how much main memory that can still be used. Now we look at those requirements one by one. So as you know, relocation is the requirement that enables for process to seamlessly swapping in and out from secondary memory, which is your hard disk, and into the main memory, which is your RAM. Okay, why does the process needs to be swapped in and swap out? If you remember, in our earlier chapter, we have the changing of states between the process when it is actually waiting for the availability of a certain variable of signal or a certain resource. Hence, active process are in the main memory, and then inactive process are swapped out into the secondary memory. So, in order to have this seamless transition or swapping of location, OS must fully understand or must be able to do the relocation of the process segments and page into this location whenever it is needed to do so. This first requirement is very important because usually we have limited memory space and it can only be accommodated by active processes. So having this requirement is very important because without that, process cannot be effectively relocated into this location and might cause a system failure. To illustrate the complexity of this process, just look at the diagram in this slide. So just imagine this is actually a representation of a process image where you have the program information, the data information, and also the stack information related to a process. So this process information need to be relocated according to the needs of the process instruction. So there is the information of the location of process control information, the execution stack, and the entry point to begin the execution of processes. Because remember, if a process is actually being suspended for a certain time or being blocked, OS needs to remember at which instruction does the process actually being blocked before it can proceed to the next part. Okay, so these are some of the examples of why this information need to properly keep track on to enable the process to execute, stop, okay, and then continue freely during the queue in the main memory and also after that outside the secondary memory. Another complexity, of course, if you remember, is the concept of virtual memory and also physical memory. Virtual memory is a representation of the memory availability or the total number of memory available that can be used. While on the other hand, we have the actual physical memory where the memory availability or slots that can be used is actually scattered all over the memory location. So in order to have a very easy to understand representation, OS needs to actually keep track of this mapping of location of the slots that is being used by the processors, because if you remember, we have many processors at the same time. So each of these process block is actually being represented uh, virtually to the human consumption, and at the same time it needs to be cross-referenced in the actual location, that is the physical location in the main memory. Because remember, the main purpose of the operating system is to help user to easily understand what is happening inside the system, or perhaps if they want to actually execute the process, they know they can actually execute it because there is enough main memory space that can be used by their application. So this task is also needs to be uh, effectively managed by the operating system to ensure that their objective is satisfied. The second requirement is having the protection capability in order to protect the use of memory space by processors. So before process can actually accommodate certain memory block or space that is free, it needs to get the permission from the operating system, and then it can only use the memory block that is free. So memory reference will constantly be checked from time to time by the operating system to see which memory block is free and which memory block is actually occupied by a certain process and which process may actually accommodate this free memory block. A process cannot simply use whatever free available block in the main memory without getting the permission by the operating system. The third requirement is having the sharing capability, because usually, unrealistically, processors sometimes share resources such as data and input from the user. So whatever data is already there in the main memory can be used across program. For example, when you do copy and paste, okay, you are actually copying and pasting whatever information that is already there in the main memory at that particular time. So let's say you are copying from the browser, Firefox browser, and then that data you actually paste it in the Microsoft Word at the other time. So this is one of the simple example of the sharing capability. Okay, it enables the sharing between the already available data across processes so that you cannot waste space in the main memory to actually accommodate the same type of information. So that information is referenced at another location and the copy of it is being used by the other process that needs it. Number 4 is having the requirement or to enable having the logical organization of this memory space. Memory is organized as a linear one-dimensional sequence of bytes. So for example, if you have 100 megabytes of memory available, it is represented just as that. It is being visualized as one-dimensional or one linear sequence of the available memory block. But in fact, it is not as simple or as beautiful as just that representation. Okay, this is what we call the logical organization, and this information is usually being used by the user. On the other hand, we have the capability to have physical organization, and then this physical organization must be successfully mapped out to the logical organization. Physically, in your main memory, the available spots is not as pretty as you've seen in the logical organization representation. Usually, if the OS set we have 100 megabytes of space that can be used by the process, it simply means that we have perhaps 10 block of megabyte memory here, and then perhaps 80 block here, and then 10 block another location. So physical organization cannot be given to the user to actually do it manually, because you have so many segments of this memory block that must be managed by the operating system, and in order for it to do that, it must do proper estimation, do the swapping in and out, and this is hard for the human to do. This is where OS must fulfill this requirement to have a very good representation in the logical organization of memory. Now, continuing into part 2, we look at one of the methods being used by OS in managing memory. So, in part 2, we are going to look at the concept of memory partitioning. Before going further, we look at the concept of virtual memory. If you remember, in the previous section, we are actually seeing the concept of logical organization and also the physical organization. Logical is where we see the available memory that can be used as a linear set of available block. So for example, if the OS say that, okay, this particular process can actually use 100 megabyte of memory block, okay, so in the actual physical organization, that uh, memory block is actually scattered physically. So you can have 10 block here, we can have 70 block there, and we can have perhaps 20 block in another location. It's not as pretty or as neat as the logical representation. So the concept of virtual memory is just like the concept of logical organization of memory. So this logical representation is being seen as a continuous block that can be used. So the process or the user sometimes needs to see the availability of this block, because they just need to know how much block that can be used regardless of where is the location of this block actually physically in the main memory. So the OS need to actually represent this continuous representation of virtual memory, while at the same time map out each available block physically to the physical memory. Modern operating system uses the concept of paging and segmentation for memory management. We will look at that concept later on in this lecture, but for now, we are going to look at the concept of paging in memory management and why is it first of all being used in older and obsolete operating system. We need to get an understanding of how memory management used to be done to get an appreciation of what is being done nowadays. So first of all, we look at the concept of fixed partitioning. In fixed partitioning, the memory block is actually represented in some of the predetermined space. So if you see here, so let's say we have this amount of memory that it can be used. So each available block is sized equally. Okay, so you see that this one is 8 megabytes, another one is 8 megabytes, and until the end is 8 megabytes slots that can be used by the process that needs to execute. So this equal size partitioning, okay, must be accommodated by the active processes. So the operating system can swap out a process if all partitions are full and no process is actually in the ready or running state. So this is basically the available slots, and coming process must actually accommodate this slot when needed. If the memory block is already full, then the coming or the inactive processes must be swapped out from this space. So in fixed partitioning, as long as there is available slot that can be used by the process or new processes can continue to come in and accommodate those slots. Only if all those slots are already occupied, then a swapping in and out must be done to accommodate new processes. However, this approach in fixed partitioning comes with a certain disadvantages. Because if you remember, each partition is already fixed in size, so a program sometimes may be too big to fit in a partition. Hence, an adjustment needs to constantly be done in order for the OS to determine which partition size is optimum that can be used by the processes. And also, secondly, memory utilization may not be very efficient. First of all, because any program, regardless of size, occupies an entire partition. For example, one process perhaps just needs 4 megabytes of space, but it needs to go into the 8 megabyte partition already allocated by the operating system. While on the other hand, perhaps one process might just need to use 1 megabyte of memory space, but it still needs to occupy the 8 megabyte partition already allocated by the operating system. Hence, there are a wastage of space. And from that comes internal fragmentation, where you have this wastage of space that is not being fully utilized by the process. Another approach in partitioning is the unequal size partition. So in contrast to the first fixed partitioning where you have equal size, now you have an approach where you have unequal size partition that can be used by processors that perhaps need to use specific or very near to the size allocated by the process. So now, instead of just having the same 8 megabyte of partition for every process to use, this time it has a variety of memory partition that can be used by process as needed. So perhaps smaller process can use the 2 megabyte partition, and bigger process can use 12 or 16 megabyte of partition. So now we have a certain choice of partition that can be used by these processes. So is it a perfect implementation of memory management? What do you think? So again, it comes as certain disadvantages to the process that wants to use it. First of all, the number of partitions specified at system generation limits the number of active processes in the system. So let's say you have a number of brick processes coming in. Of course, it cannot use the smaller partition already placed for smaller processes. And if you have smaller process coming in, it will not fully utilize the spaces that is allocated for big process. So wastage can still happen, and a number of active processes that is big that cannot accommodate the partition that has already been there to allocate small processes will constantly being blocked. So then we come to the concept of dynamic partitioning. So in dynamic partitioning, partitions are variable length and number. It is given according to the coming processes that is allocated by the operating system. So let's say a process that the first process needs only 4 megabytes of slot, then only that slot of partition memory will be given to the process to use. And then the second process perhaps need to use 8, then the created partition will have 8 blocks of memory to use. This continue according to the needs of the process. Is it an optimal solution for the memory management? What do you think? So in order to illustrate the effect of dynamic partitioning, let's look at this diagram. So in diagram A, if you see here, you have a very available space that can be used by processes. So let's say you have process 1 coming in and it just needs 20 megabyte of memory slot. So that first 20 megabyte of memory partition is given to process 1. And then secondly, process 2 comes in with a request of 14 megabyte of memory. So again, because we have available slot to use, then process 2 can use 14 megabyte block of memory. And then the third process, we have process 3 with 18 megabyte of memory. And then we left with 14 megabyte space left in the main memory. Now, what happens after that? Now, imagine after all three processes has already accommodate the memory slots, now only 4 megabyte of space is left. So what happens if another process wants to come in? Let's say process 4. Okay, so one of the inactive process or perhaps process that is being blocked need to be swapped out. So in this example, process 2 is being swapped out. So leaving the gap of 14 megabyte of space already left by process 2. Then process 4 can come in and use the available block that is already left by process 2. So process 4 is here using the available block of free memory. Okay, so after a while, let's say process 1 finishes. So previously it was using 20 megabyte of block. Now you have a 20 megabyte block that is there that can be used by another process. So now we have 20 megabyte block that is space available to use, and then we also have the balance of 6 megabyte from the previous one, and then we have 4 megabyte here. Okay, so let's say after a while process 2 needs to come in, so now process 2 will use this block now. Okay, and then you have this balance of memory partition that can be used, and also this one and also this one. So did you see any problem in this implementation? What is it? So as this example show, this method of dynamic partitioning, it starts out very well because you can have process that is coming in that can have custom partition size that can be used by them according to the needs. But after a while, let's say you have 10 processes coming in, and perhaps after a while the previous process is leaving the memory partition, you will be left with certain fragmentation of the balanced memory space. So this is what is called the external fragmentation. So let's say previously, okay, like this one, you have 20 megabyte of space being used, okay, and then after that, you are left with only 6. So the number of active processes that can actually use these external fragments becomes very less and less, and the OS needs to constantly ask the CPU to do the compaction to enable for the available memory block to be added up together and be available for another process. So the active process that can come in becomes very limited, and the time it needs to actually assign this available block becomes more and more, because there need to be some adjustment to enable this memory block to be added together and make it available to the next coming process. So from dynamic partitioning, we have the problem of external fragmentation, because we have small fragments of memory left by the previous process, and memory utilization becomes less and less because you cannot have an ideal memory block that can be used by the newer process. And then we need to constantly have the process of compaction, where those fragments that is being left need to combine together to be available to the coming process. So this consumes CPU time. So instead of just executing process, now the CPU is there to actually do the compaction and identify which memory block is available for the process to use and compact it together and assign to newer process. So before we go further to the next part, okay, have a 5-minute break. Perhaps review back what we have learned previously. So try to look back at the concept of partitioning and how each concept of partitioning try to improve the previous one. And then what is the weakness that have already been improved by the other implementation, and what is the weakness on each of the implementation there in terms of partitioning that is being used by memory management method. Okay, so we take a 5-minute break here, and then we continue to the next part, which is placement algorithm. Now, for this part, we are going to look at the placement algorithm. So basically, what are placement algorithms? If you see previously in the partitioning, we have perhaps some variable space of partition that can be used by processes that is coming in. So how are we going to decide which process goes where? So this is where the placement algorithms comes in. So in terms of placement algorithm, we have 3 approaches. We have the best fit, first fit, and next fit. Okay, for the best fit, it will choose the block that is closest to the size of the process, while the first fit, it will scan the available memory partition and go into the first one that the process that can actually go to, while the next fit will be based on previously where has the other process gone to, and from that location it will go to the first available slot that is can be used. Okay, I will illustrate it in the next diagram. Now, take note at this memory partition diagram. So, in this diagram, you will see that there are variety of memory partition that can be used by processes. Okay, and also in this diagram, it stated that the last allocated block happens in this location. Alright, so let's say in this example, okay, you have a 16 megabyte allocation request coming for the new process. So it's based on different placement algorithm, where will this process go in this slot. So which slot will be selected? Okay, so the next coming is 16 megabyte request of allocation. So these are the space that is available. Okay, so where will the process go? So let's say if using first fit. So first fit, as the name describes, it will scan the entire block of memory. Okay, and the first one that it can fit into, it will actually go there. So in this case, First of all, it scan this one. Okay, can this actually fit into the 16 megabyte allocation? No. Secondly, it check this one. Can the 16 megabyte allocation fit here? No. So, third, can the 16 megabyte allocation request fit here? Yes. So, it will choose this location if it uses the first fit approach. Now, let's say it uses the best fit approach. So, the best fit will look at the closest value of partition that a process can go to. So, it will check each and every one, okay, and compare from each available allocation, okay, which one is actually the closest to the process request. So it will look this one, is it the closest or not? This one, not. Okay, and then it needs to actually analyze each and every option. Only it will decide. Okay, after going through all the option, it will see that this 18 megabyte block is the closest to the request. Hence, the best fit will go into this location. Now, the last one is next fit. So, how will next fit actually do it? Okay, next fit actually, first of all, is based on the previous allocation location. So, in this example, the previous allocation location is here. Okay, it works actually just like first fit, but it will start the searching from this location. Okay, so we look at here. Can it fit there? No. Can it fit there? No. Okay, can it fit there? No. Can it fit here? Yes. So it will go to this location if it uses the next fit algorithm. Okay, so you need to understand the difference between first fit, best fit, and next fit. Okay, so what is the advantages of each and every one of this approach? So in terms of performance, first fit is the most simplest and usually the best and fastest because it simply searches for the first available block that a memory can use. Second in place in terms of performance is the next fit because it needs to actually check previously where was the previous one process actually allocated and start the search from there. Okay, so what do you think is the performance of the best fit? Is it actually better than first fit or is it actually worse? What do you think? So best fit in terms of performance comes out as the worst performance among the three. Can you guess why? Okay, if you remember in the previous example, the best fit algorithm need to actually see all the available option available in the memory partition. So it will check every available space that can be used by the process and then compare that value to be which one will be the closest to the memory request. So the time is being spent on comparing each available option before a decision can be made. Compared to the first fit, it will just check one by one, but the first one that is available, then it will go there. But best fit, it will need to check every single memory partition and then do the comparison, and then only it will need to accommodate those memory partition that is available. Hence, that's why best fit is the worst performer of all between the three. So another approach to fix the downside of fixed and dynamic partitioning is the buddy system. Because there are limitations to the fixed and dynamic partitioning scheme, so we have a compromise in terms of the buddy system. So how is it done? So simply put, the buddy system is created to actually save the CPU processing time in order to find the next allocated space that can be used by incoming process. If you remember, in fixed partitioning and dynamic partitioning, the most time is being used actually to find the most optimal space available that can be used by the process. So this is where the buddy system comes in. So how does it work? So I will demonstrate to you in the next part so that you can easily understand how this works. So what buddy system is doing is combine the method of fixed partitioning and dynamic partitioning in one approach. It tries to fix the CPU time that is already spending in order to find the best possible partition that can be used based on the request of the process. So based on the request, it will make the closest partition that can fit into the process request. So for example, we have a request for 100 KB of process space, 240 KB, 64 KB, 256 KB, and 75 kilobytes. So in this example, we have 1 megabyte of memory block that can be used by multiple process. So in a buddy system, this memory block is divided into a pair of buddy. Okay, so in this example, 1 megabyte, first of all, is divided into two portions, 512K and 512K, another half. So the first request is 100 KB of memory block. So it will need to create another buddy that is closest until it gets to the point that it can fit to the 100 KB of memory request. So from 100 to K here, it will leave there. So the second buddy, okay, again, it will divide into two. So 512K divided into 2, you have 256K and 256K of memory block. Still, it's not close to the 100K request. So we have two buddy here. Now, this buddy is again separated or divided into two. Now you have 128K and then you have 128K. So 128K of memory block is the closest that it can create to accommodate the 100 KB of memory request. So process A, the first request of 100K, can actually be put into this memory block. So the second request, 240 KB. So basically 240 KB, where can you put it? So based on the already available or created buddy, so you already created this one is free, and then also this one is free. So that's why the second request can be put into the 256K memory block that is already created. Now, after that, you have a request of 64K. So 64K, where can you put it? So you have this space still available. Okay, so this space can be further divided into two more blocks. So you can have 64K and 64K. Hence, the third process can go into this block. Alright, and then after that came the next request is 256 KB. So where can you put it? So currently this one is still free. This one is also still free. So because you cannot put it here, so this memory block can be further divided into two. Hence you will get 256K and 256K. So after this one is created, so you can put this request into this block. Now, what happens if a process was released or perhaps finished? So once the process has finished, so let's say in this example, B has finished. So this slot that was previously being used by B will be released. Now you have this much space available. And then after that, let's say after B is finished, you can release A. Okay, after A is finished, you can release A. Then you have this much space available. And then you can say, let's say lastly, you have the request for 75 KB. So 75 KB, where can it go? So 75 KB, based on the previously released one, it will look for the first that is closest to the value. Hence, the space that was vacant by A now can be used by E. So E now resides in this memory block. And of course, after C finish, now C will release that. Okay. if you see after release of C, you can see it here. Okay, and then after E is finished, now it will release that. So the advantage here is that this compaction can be done much more faster because it's done using the most closest body available. So instead of randomly choosing the farthest location, for example, it will always use the closest body that it can accommodate for newer processes. So it's basically try to improve the shortcoming in dynamic allocation and fixed partitioning by creating the body system. Okay, it's not so much on very improvement in terms of space allocation, but it wants to help the CPU to spend less time in finding the ideal space based on the memory request. Okay, so when you have this body, so this body can actually collect this information, and those information can easily be passed on into the CPU to decide which process can actually accommodate based on the closest value, okay, that is already available that a process request can use. Okay, that is just one of the implementation or why body system is created in partitioning method that can be used for memory management in this approach. So if you still cannot grasp this method, so return back to my explanation earlier and see how body system is being done. Simply put, in a body system, the memory block is always constantly divided into two pair of bodies. If let's say the created body cannot accommodate the process request or still big enough, then the body will be further divided into two until it will get to the closest possible value. This is basically a combination between the fixed partitioning and dynamic partitioning approach. Just like I said earlier, the reason why we have a body system if we want to actually improve the CPU time in finding the next possible fit for the process request. Of course, the most effective of memory management approach is using the paging and segmentation approach. So why is paging and segmentation being used for modern operating system? That is where we will see in the next section. Okay, so before we continue, please go through again what we have learned today and try to understand why these methods are created and what are the advantage over the previous one. Okay, you can take a 5-minute break before you continue to our next part in the slide. Virtual memory is the one approach that is always being used in modern operating system. Usually, in concept of virtual memory, it uses the method of paging or segmentation in order to allocate memory from the physical into the logical allocation. So how is it done and why is the method far more superior compared to the partitioning approach? This is where we are going to see in this section. First of all, you need to understand some of these terms. The term logical address actually refers to a reference of the actual memory location in the physical location, while the physical or absolute address is the actual location where that address or that memory block is located. For example, logical address is just a reference to the actual location. For example, I say that this process is located in box A. And then box A actually pointed to the actual address, which is on the actual main memory location. Okay, so logical address is just a representation of the actual location, while physical address is the actual address where the memory resides. Why it needs to do this? Because remember, logical address is where you have a continuous block of memory available that you can use. For example, let's say I say that you have 8 megabyte of memory space that you can use. And in terms of representation, I just show you, you have this much space that you can use. Okay, but I didn't say actually in this 5 memory block location that memory block that you can use, where is it actually? So like I said earlier, one block can be from location A, and then second block can be from location Z, and then perhaps the third block can be from location X. Okay, what you need to know is that how much location that you can actually use. You don't have to care where is the actual location for the block that you can actually use. That portion or that information is needed by the OS but not needed by the process. Okay, that's why we have logical address and then you have the physical address. Logical address is the one that's needed by the process and the user, while the physical address is the one that's being used by the OS in the background. Okay. So in order to understand what is the difference between paging and segmentation, just understand that paging and segmentation is how process instruction or process information are being stored. So in terms of paging and segmentation, first of all, paging are chunks or partition of a process. So let's say your process for the size of perhaps 4 megabyte is divided into 4 chunks of pages. And then the number of available blocks inside the memory is known as frame. So how many frame of memory can actually allocate those 4 pages of process? So this is just the thing that OS needs to manage. It is actually to accommodate how many space of page of process into this available frame of memory in the memory location. It's just that. It's very straightforward actually. So how is it done? You need to get this concept very early on, which is the concept of pages and the concept of frames. Pages are the distribution of your process information, while frame are the actual block in the main memory that you can actually accommodate or use. So in terms of memory management, the task for the OS is to try to accommodate as many pages of process as possible into the memory frame. So in order to understand how logical address is being used, see this available memory block with 15 frames of memory. So let's say you have 4 pages for process A, and then you have 3 pages of process B, and then you have another 4 pages of process C that is actually being used. Now let's say after a while B is perhaps finished its turn and it leaves the memory block. So now it has 3 available frame of memory here and 4 available memory frame available here. Now let's say the next coming one is process D with 5 pages of memory. So where can actually we put process D? Okay, so this is one advantage of the paging process. Now, because each process is divided into pages, now each pages can be separately put into those frames. So you can put the first 3 portion of pages for D here, and then the remaining pages for process D in location 11 and 12. So this is one advantage of the paging process, where you can actually allocate process in not a continuous manner. What it needs is just a reference of where is those page actually located. Because you have so many separate pages, now the problem here that you need to actually solve is how do you actually collect those page information and where does those page is actually mapped to this frame number. So which page go to which frame? Okay, so this is where the paging implementation must be done, which is the collection of those page number and map it to the correct frame number. Thus, paging approach, you need a data structure known as the page table. It needs to actually map each separated page of a process to a location or frame that you use in the main memory. So this page table will act as a reference that can be used by the OS and CPU in order to find those pages where is it actually located physically in the main memory. Now, as a simple representation from our previous example, now we look at how does a page table is actually being used. So if you remember in our previous example, you have this frame number from 0 to 14, and then you have the page number which actually reflect the page number from each process. You have process A, process B, process C, and process D. So in the process table, in the page table, you have this information. So for the process A page table, it will actually tell the CPU, okay, for frame 0 until 3, okay, we have this portion or the page for process A. Okay, while for process B, we don't have the information because process B already depart or removed from the memory frame. And then you have process C. So process C page table will contain this information that will tell the processor, alright, currently process C is using this memory frame. Okay, so this, okay, we cross-reference this. We see that process C is currently in frame 7, 8, 9, and 10, which is reflected in this diagram. And then for process D, okay, is using frame 4, 5, 6, and frame 11 and 12. And then it will also have the information of free frame list, which is frame 13 and frame 14. So basically, a page table contains a reference with regard to the page information of a process and map it to the correct frame of the memory. That's it. Now, notice that a simple paging described here is similar to fixed partitioning. The difference is that the partition, although rather small, okay, it can accommodate a large number of processes because this time processes are divided into pages, and then this allocation of frame does not necessarily mean that the process must accommodate it continuously. So the process, because it's divided into pages, it can accommodate many space available and not in a continuous manner. For example, in D here, so D can actually accommodate this location 4, 5, 6, and 11, 12. Okay, it doesn't necessarily have to be in a continuous manner, and this, of course, can be an advantage because realistically, you will not have a continuous block of memory to be used. So that's why in a paging approach, you have process that is, first of all, need to be divided into pages, and then those pages need to be allocated to the suitable frame. So this, of course, is an improvement from the partitioning approach that we see in old operating system. So the next question is, how do you actually translate the address from logical address to the actual physical address? So this example, in the operating system, okay, you have the logical address example here. So for example, let's say we have a 16-bit logical address for a process. So in this example, okay, 6-bit is being used as the page number, while the 10-bit offset is the address. Now we want to find out physically where is that page being allocated. So now we have the process page table. So we first divide or break apart the logical address, but you must have the bit page information first. So usually it will tell you whether the first 4-bit or the first 6-bit or the first 8-bit is being used as the page number. In this example, we are using 6-bit page number. Okay, so from the 16-bit logical address, you break off the first 6-bit. Okay, so in this example, the first 6-bit, this one, from this location 0, 0, 0, 0, 0, 1, okay, is the page number. Now you need to cross-reference this information with the page table. So from the page table, you have reference 0, reference 1, and reference 2. Okay, from this information, it tells you that, okay, you need to actually refer to the page table in number 1. So you refer to number 1, and then this is the value for number 1, 0, 0, 0, 1, 1, 0. So what happens next? You take this value, alright, and then you straight away replace this value with the value that you have here. Okay, so now this value is the physical address for that process. So now you have 0, 0, 0, 1, 1, 0, which you get from the process table, and then the last 10-bit is the one that you take from the first logical address. So this is how you translate from logical to physical address in the paging approach. Okay, the information that you must have is the first logical address, and then how many bits are the page number, and then the remaining page number, okay, you cross-reference it with the process table. So in this example, you take this value, reference here, you take this value, you replace this value. So from this value in the logical address, this is the actual physical address for that page of process. Okay, so if you don't get what I'm explaining here, try to review back what I've explained, and perhaps if you need further explanation, you can ask me later on. Now, apart from paging, we have the method of segmentation. If in paging we have an equal amount size page, now in segmentation we have a variety of sizes of segments. It's still a part of a process, but this time there will be a variety size segment with regard to the process information. If in paging you have the same size page for all the process information, now you have a variety of segments with variety of sizes with regard to the process information. So basically, in segmentation, addressing consists of two parts, which is the segmentation and also the offset number. Because segment consists of variable length of process information, so the addressing is a bit different. But still, there is a reference that is used if in paging we are using page table, but in segmentation we are using the segment table. So how is it done? We will see in the next part. So the question is now, how do you translate a logical address in segmentation to the physical address? So this is how. Usually, in order to translate from the logical address in segmentation, you need to have the process segment table. Okay. Notice something different compared to the page table. This time we have the length information. Okay. Instead of just the information of the offset they want to change, now we have the length information, because in segmentation we need to actually know how big of a segment size that we need to actually map into the frame of the memory. So in this example, let's say we have a 16-bit logical address given. So from this logical address, how do we actually translate this logical address to find where is it physically located in the main memory. So let's say in this example, the first 4-bit is the reference number. Okay, just like before, we need to actually find the first 4-bit from the 16-bit logical address. So we separate the first 4-bit, then we will get this reference number 0001. Okay, so translate this number and find it from the segment table. So from this segment table, we find out that for number 1 reference, we need to use this information. Okay, so from the logical address, you separate this information first. So you need to keep this balance of 12-bit offset, because you need to do this later on in order to translate the logical address into the physical address. So the first 4-bit is the reference. We need to actually cross-reference that number to the segment table, which in this example, it refers to this one. Okay, so what you need to do is take note of the base number information here. Okay, so after that, remember the 12-bit that you keep earlier. So you take this value, you add to the base value, which is referred here. Okay, so what you get is, you will need to add the first balance of 12-bit offset. You add it to the number that you find here. Okay, so as the result will be the actual physical address of the main memory for that segment. Okay, so remember, if in page table or in paging method, we are actually just swapping the value that you find from the reference. But in segmentation, we actually need to add the value that we found in the segment table. That is pretty much the difference. So if my question, I need to ask you from the paging method, find the physical address, or found from the segment method, find the physical address, you need to actually understand how to do this. Because this is actually just to simulate what does the OS need to do in order to translate from the logical address to the physical address in order to find the actual location in memory where a process information might be kept. As a conclusion, for this chapter, you need to remember why or what is required from the operating system in order to have an efficient memory management implementation. So remember, you have the relocation, we have the security, we have the logical, and also the physical implementation of memory management, and why is it needed. And of course, what is the difference between partitioning method and also paging and segmentation approach, and what is the role of the placement algorithm within those methods. So after the end of this session, I will give you some exercises to try to apply what you've learned today. Okay, and if you have any question, feel free to ask me later on to see whether you have understood what we need to learn today. So I hope it has been beneficial to you, and I thank you for joining the session. Till the next session, thank you very much.